Good afternoon, everyone. If you have doubts, earlier morning we discussed about the programming of the DCOPF. So if you have any doubts, please ask them. Okay, so we will move now to ACOPF. So while doing DCOPF, we assumed that are you on?
Yes, sir. Yes.
Okay, so like for DCOPF, we assumed that resistance is negligible, so no losses has been considered. So no losses in the system. We assumed no reactive power as well. Okay, and voltage magnitudes are equals to 1, and change in angle is very small. Okay, so close to 0 or tends to 0 basically. So we can say it is tends to 0. So those were the conditions for DCOPF, right? Now in ACOPF, we will not consider these constants, and it is without any assumption, we are going to solve it. So how can we do that? So okay. So again, the objective, we have set an objective. So let's keep the same objective. It's a minimization of cost function, right? So it's I will keep the objective function equals to minimization of cost only. So it is, and that is equals to the same objective function. So we will keep I equals to 1 to n ci, and let's say use PGI. Okay, so that we don't get confused sometimes. So this is our objective function. Then we had a constant. So earlier, how many constants were there, like in DCOPF? So we had active power balance equation. We had power flow limits, and then we had generation limits and angle limit. So these were the this was the DCOPF. So we'll also follow the same thing for ACOPF as well. So what I will do is, first of all, I will write down the active power balance equation. So for each node, we have to write it down. So it is basically PGI minus PDI equals to summation over J equals to 1 to N and PIJ. Now for ACOPF, we have to consider some parameters. So like we assume that voltage is not one, so the voltage at any bus will be vi angle delta I. Okay, and this will be I considered instead of delta theta, but let's say delta I is the voltage, and then we have active and reactive power. Apart from that, we have a bus admittance matrix. Okay, which y bus. This bus admittance matrix gives the entire topology connection, because like this Pij, if you are a studied power system, the power between I and J can be given by this very simple formula for the polar coordinate system, that it's Vi magnitude, Vj magnitude, Y bus Ij. Okay, so Y bus Ij magnitude, then cos of theta Ij minus delta I plus delta J. Okay, this was the power balance equation, and this power balance equation we have to write down for all I set of nodes. So we have to write it down for all number of nodes available in the system. Here, if you say what is PGI, so PGI is so power generation is basically PGI plus J QGI, active and reactive power. Similarly, the demand is also active and reactive. So that is PDI plus J QDI. Okay. So basically, these are known information, and the voltage we have already discussed that the voltage will be some voltage angle delta. So VI is basically the magnitude of the voltage at any bus I, and delta is the angle of the that particular bus. Okay, then we have a Y bus matrix. So the theta Ij is actually the angle of element Yij. Okay, so okay, let's not use Y bus. I will use Yij for this particular part. So it is basically, let's say we have Yij mod cos of theta Ij minus delta I plus delta J. So this formula is already known to us, that okay, this is the active power flow between bus I and J. So this we are going to write down for I equals to 1 to n. The similarly, the reactive power flow formula is also given like this: QGI minus QDI equals to summation of J equals to 1 to n and QIJ, and Qij is given like this: J equals to 1 to n minus of Vi, Vj, Yij magnitude, and instead of cos it will become sine theta Ij minus delta I plus delta J. Okay, and this equation again, so this equation will be written down for all I, and this will also be written down for all I set of n. So The name of this equation is basically active power balance equation, or you can also say active nodal power balance equation and reactive nodal power balance equation. Okay. Apart from that, so as if I compare it with the DCOPF, the cost function is same. We are also using the same cost function. Power flow generation. So, like active, like we only had active power balance equation in the DCOPF. Now we have two power balance equation. One is active and another is reactive power balance equation. Then let's talk about the power flow limits. So, what will be the power flow limits? So we have defined Pij above, that Pij will be equals to Vi Vg Yij cos theta ij minus delta ij and plus delta j. So I will define the same thing like active power flow limit. And active power flow limit is Vi Vj Yij. So all of these are magnitudes, right? And then we have a cos of theta ij minus delta I plus delta j. So this should be less than whatever is we have limit by power flow ij maximum, and whatever is the limit we have here power flow ij minimum. Okay, so these are the limits we have mentioned, that okay, these limits are there, and this we have to write it down for all ij pair, which is set of lines. Okay, so whatever is the number of lines, for those we have to write down. And generally, if you know, there is no limit on certain lines, like we consider that okay, these will be relaxed all the time. So we only focus or write these equations for the lines which have certain maximum limit. Okay, so these are the power and basically generation. Okay, wait. Now, if you look at like power flow limits, so instead of power flow limits has been mentioned here, generally we have only active power flow limit, and we do not have any limit on the reactive power. So, and sometimes it is only like apparent power flow limits are available, but let's say we can write those limits here. Now, generation limits. So next is generation limits and voltage limits. So generation limits are instead of like earlier we had PGI, which is less than equals to PGI max and PGI min. This has to be write down for all I set of generators. Now we have active power as well. Sorry, reactive power as well. So I will write down this same equation for reactive power as well. So it is QGI min, and this has to be write down for all I set of generators. Next is so generation limits has been placed, voltage limits. So I will put some voltage limit, okay, and that voltage limit is basically like whatever is the Vi maximum limit and whatever is the Vi minimum limit. Similarly, the angle instead of theta we are using delta here, that we will put like pi 2 minus pi or pi by 2. Both of these equations will be written down for all set of the nodes. Like for all the number of nodes, we will write down these equations. Is this clear? Now, if I ask you one question, let's say for a 14 bus system, how many voltage magnitude constraints will be there for ACOPF? So let's say there are 14 bus system. So yes, it's a two. Earlier also we discussed that it's both maximum and minimum limit. So two limits for each node, and if there are 14 nodes, then there will be 28 limits at each for each voltage. I think this is fine. I think we don't did we left anything? So like if I look at the DCOPF, the objective function we defined for AC as well. Power balance, so it is active and reactive both. Powerful limit, so generally it is for active, so we have defined that as one. Then generation limits for active and reactive. Voltage, so voltage limits is for angle and magnitude, both has been defined. So I think this is it. Apart from that, one important equation is missing, that is our delta reference should be equals to 0. Okay, so this equation is equality constant is also there, that the angle of the reference bus should be equals to 0. So this is the a simple AC OPF formulation. Do we have any doubts here in this particular formulation? So these are my power balance equation. This is line flow limits. Then we have generation limit. So these two are generation limits. And then we have voltage limits. Okay. So now if we try to, like write down the code for this one, can we do that? So earlier today, we basically solved, like learned how to use fmincon function for DCOPF. So we are going to use the same function for ACOPF as well. But let's first of all check whether it is linear and non-linear. So if I look at, like, the very last equation, it is quite obvious that this is only, like, equality constant, so it is linear. All the voltage limits are linear. It is quite obvious and visible clearly. So these are the limits. Again, generation limits are also linear, but these three equations are these three set of equations, basically like the power balance equation, both active and reactive. Okay, so then line flow limits. So this is our line flow limit. These are basically active power balance equations. Okay, these are power balance equation, active and reactive. So these are highly non-linear because you can see there are cost terms and there are multiple uh, voltages are being multiplied. Can anyone tell me what are the variables here? Because without knowing the number of variables, it is very difficult to program it. First of all, you need variables. So what are the parameters and what are the variables? So Vi, Vj and theta Ij. So these are the variables, correct? So voltage magnitudes and angles, voltage angles are variables here, and whatever is the rest is parameters. So if I look at this particular function from the very beginning, let's define the variables as well as the parameters. So first of all, we have a cost function, and cost function we all know that we are using a quality cost function. So it's a pi square b p plus c. So the parameters will be ai, bi, and ci. So this input is needed first of all. Then if we move to the second, like equation, which is active power balance equation. Then we can see PG. So power generations are basically like we are doing optimal power flow. So PGI and QGI will be variable. So power generations is variable, but the PDI and sorry QDI will be parameters. This is the input to the OPF problem. So this is known. Then we have VI, VJ. So voltages are again variable. So VI, VJ. Here the angle of voltage is not theta. I have assumed delta. Earlier I assumed it theta. So delta I and delta J. These are basically the variables. And if I look at the parameters, so Y ij angle theta ij. So for a particular element of fibers, whatever is the angle of that particular element, both of these are basically parameters. Apart from that, so this is I think it for the both the equations. Everything has been covered in this. Now if we look at the third equation, one more term is there, which is power flow max between I and J. Uh, then anything else is like there for parameters in sir in OPF there state and control variables. I think here we have neglected several parameters. Okay. How what is the difference between like yes angle should be 0. What is state and control variables? So I will come back to you. First of all, just let me just define what are the different parameters and input. So we have like these are the variables. Apart from that, there are no variables. Now let me define some parameters as well. More parameters. So what are the other parameters? Parameters are basically PG max and min, UGI max and min, VI max and min voltage magnitudes. Delta is already we already placed in the optimal. It's basically pi and minus pi, and another is 0. So that is also part of there. So we don't need like input. It is always 0. So that is also reference angle we have already placed as a 0. So these are the different parameters and different variables. So variables are basically the voltage magnitudes, voltage angles, and active and reactive power flow. So these are the different variables we have. Now, can we write down a code for this basically? My question is like, have you tried to solve the assignment which was given? Anyone? Yes, you can like raise your hand and I will unmute you. So
Hello, sir.
Yes, please.
No, sir. Actually, I have not solved the assignment.
It's okay.
I'll solve in
It's
the evening.
fine. Like you can try to solve it. I will discuss the ACOPF, so you will be able to like more comfortable that how we can solve this thing. And in the meanwhile, one very good question came. So I will quickly go through some PPTs basically. So yes, so I will take 10 or 15 minutes more to just look at some certain equations, like how the power flow analysis works, and then we will talk about like how to write down this very complex piece of code with the help of uh, MATLAB and the function fminco. Okay, so I will let me share you my entire screen with you. Uh, is it visible? Right? So,
Yes, sir.
Kush, can you show me the questions basically? Sorry, chat. I want to see the chat here. Okay, and the upper one. Yes. So in the OPF, there are state and control variables. I think we have neglected several parameters. No, I will explain you what are the basically like state variables and what are the different control variables. So I will ask this. Then can you go down the last question? Yes. After relaxing the non-linear variables into linear quantities, solving is very complex as non-convexities are there as well. No, but we are not basically relaxing any non-linear variables. Can you
Yes.
unmute? Sorry.
Yes, sir. I'm on.
Yes. So, like, can you ask what is your question? Like, what do you mean by the you put in the chat?
No. Sir, the BI into VJ, the product is nonlinear. So we can assume another variable and make the limits in
Uh,
different
I
forms.
I agree, but like if we relax them and to make it linear, so that already we have already discussed. Like DCOPF is a linear form of ACOPF only.
Yes, sir.
Okay, and another there are different other ways of as well, like because this is highly generally we call it non-convex problems, and there are then we try to solve it with different relaxation like second order conic programming, and different methods are there. We try
Yes.
to use them to further relax so that the computational burden is reduced and we can obtain a global optima. But like here we are using the the basic fundamental highly whatever is the non-linear problem. We are going try to solve that only, and we are not going into relaxation like how to do different kind of McCormick relaxation as second order SOCP relaxation. So we are not going into that. Fundamental ACOPF about your state and control variable. So just to go into that, I want to focus on the power flow analysis. So what
Okay.
is a power flow analysis? You can see on the slide that it's a basic tool in power system just to calculate the analyze the power flows. Okay, so it provides information about state variables and the power flow on the lines. I will come to what are the state variables. Okay, so let's assume a network which is visible here, and if we apply a nodal analysis, we can write down Kirchhoff's current law. So all the currents can be written. So let's say some I1 I2 like at the bus 1 and 2 is there, and then we have written down uh, like all the currents we have calculated, and we have written down this Kirchhoff's current law. So, and in matrix form, at the bottom, we have mentioned I equals to Y bus into V. So, same like with a particular two bus system, if I want to write it down, so we can say that I1 is equals to Y1 V1 plus Y12 V2, and similarly as I2 is Y21 V1 plus Y22 V2. Okay, so if this is just a second, yeah. So here, if you see these current equations, they look to me very linear. That I1 equals to a constant into V1 plus a constant into V2. So I and V are variable, but these are looking very linear. But actually, uh, everything is basically in power and not in the form of current. So we have to calculate power. So
ସେ କଣ ସେମିତି ଦେଇଦେବେ ଇଏ ତା ଗୋଟେ ଥରେ ଯୋଉ ମେଲ ଆଇଡି
kindly
ରେଜିଷ୍ଟର
mute yourself. Push. Lakshmidhar Sahu, I think he is on mute. Yes, thank you. So, powers are given and node currents are known basically. So, we will calculate SI conjugate. SI conjugate. So, this voltage will be multiplied over this equation. So, we can say SI conjugate, which is P1 minus JQ1 equals to Y11 V1 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 conjugate and V2 V1 conjugate. So, this is how we can write it down. And you can see these are non-linear equation because V1 and V2 are being multiplied, and it's a complex as well. But if I move further, this Pi plus JQ Vi, we can generalized form, we can write it down like we can take Vi as a common and summation over Ik, and we can write down Yik Vk. So this is a simple formula, and then we can write it down like magnitude and e raised to power angle. So we have taken out all the magnitudes and angle out together, and further if we see, we can convert active power, so active components separate and reactive components separate. So this is Pi and Qi. So this is what I have used, like Vi, Yij and Vj. This is what so far we have written, and then cos of gamma ij, instead of gamma I use theta ij for the angle of Y bus, and then delta I and delta j. So these are the basically our voltage bus angles. So if you look at these equations are algebraic, very they model steady state operation, but they are non-linear. So we cannot solve it analytically. Another issue is for n two n bus system, there are two n equations. So like if we have n number of system, we have two power balance equation P and Q. So we have double equations. Now if you look at the variables, there are different variables, and the variables are defined as PD and QD. So these are like active power demand. Then we have voltage, and then we have power generation. So generally, we in power system operation, we call these PD and QD at the demand as a disturbance variable. So they are basically creating a disturbance in the system. Because of that disturbance, state variables are being basically changed, and then with the help of the power generation, we control them. Okay, so this is are the different variables. So state variables are voltage and angle, and then we have some generation which we basically control the entire disturbance coming from the demand. But the issue is there are 6 into n number of variables, and we only have 2 into n number of equations. Like for two bus system I have mentioned, so it is basically 12 number of variables for a two bus system, and we have only two equations. Okay, so it is very difficult to solve. So that's why, and apart from that, so if we can assume that customer demand is known, so let's say these PDQD are known. Still, if we see, then these variables are left with us. Okay, so even if we, let's say, we assume that PD and QD is known, so respectively we can calculate that okay, this much PG and QG should be there, and we can make an assumption, and then we solve these four variables. So then it is easily we can solve it. But the network losses will also occur, and this particular formation losses are basically inbuilt already. So the losses are unknown. We cannot fix power generation as well. Like, power generation cannot be placed. So we, for a 2-bus system, we had 12 variables. So first of all, we will specify the disturbance parameters. Okay. So these PDQD are specified. So I have removed them from the P part. Now specify two individual generators. So let's say we have specified generator number 2. So PG and QG has been specified. So we have removed this one. Another thing is to overcome the difference. Like voltages are always difference in the angle. It's voltage angles are always placed as a angular difference, and it is never used somewhere else. So it is always like inside the cos theta and sin theta, and that too the difference. So to calculate any variable, we need a reference, then only we will be able to calculate the difference. So let's say we have identified one angle as well. So that is, let's say the reference bus angle is kept it equals to 0. By doing so, we still left with 5 unknown basically remaining, but the equations are 4. So we have to get rid of one more variable, then only we will be able to solve these. So the another thing is like V and Q are strongly coupled, so we can choose one of them and fix the other floating. So thus we can choose basically voltage as a priori specification. After that, we will have 4 unknown and 4 equations. So this is how we come up with the 3 types of bus in a system based upon the a priori knowledge of the variables. So if like load bus, the P and Qs are known. All the P's and Qs are known. So even if a generator is there on a load bus, uh, it should be known. Then only it will be called as a load bus. But generally, like if a particular load bus there is no generator, so we can assume that PG and QG are known. They are equals to 0. So we know all the P and Q, so that is called PQ bus and load bus. And then if we talk about the PV bus, voltage control bus or generator bus, in that case, PD and QD are known everywhere. Here we basically assume that PG and voltage magnitudes are known and others are not known. Similarly, at reference bus, we assume the voltage and PG, QG are kept floating. So this is how we define the different buses. So the actual issue is these buses are like, you can name any bus anything, doesn't matter, but this is the very fundamental of like naming a particular bus as something. So why reference bus, load bus and PV buses are defined basically. Okay, so this is how we, so about your question about like there are state and control variables, and but we did not neglected anything. Everything was included in our formulation. So I think this is it from the very fundamental. Now if I again go back to my formulation, so this formulation is perfectly fine. We have defined all the variables, parameters and everything. Now I will need your help to write down this program. Actually I have written it already, so let's see whether it is working or not and how we have written it. So let's try to understand the program here. If you see,
Sir, I have one doubt, sir.
yes.
Sir, circuit breaker positions are like discrete variables. They are they means are these variables taken into account in case of OPF or these?
Uh, I think circuit breaker is not part of OPF.
Yes,
It's
the
not part of OPF. You can say like transformer taps, yes, they are part of OPF. We can model them as well. Okay. But circuit breaker is something else. It does not affect power flow.
no, sir. On-off status of
Yeah,
like
on off status is basically like whether the line is on and off.
okay.
So I'm assuming if a line is off means it is disconnected. So we don't have that line in our model.
Okay, sir. These
There won't be
these
any
are
power flow.
binary. Okay. Okay, sir.
No,
Thank you, sir.
no, you can include them. You can include them, but that will be a problem specific. Just to calculate optimal power flow, I will not consider that particular branch because it is open circuited. It means
Yes.
that branch is no longer exist for me. But yes, there are different applications. Let's say you want to identify particular branches and what will be the impact of those and everything, then we can basically model that as well in OPF.
Sir, what will be the time scale of OPF? Mostly how
So
frequently it is solved?
so the thing is, like, for a particular load we solve it. Okay, so it depends how much like, how much frequently we are solving it. Generally we solve it for each time period, and like in India we consider a 15-minute block period. So
Okay.
for that we solve it, because it is not needed like, to solve for every continuously the ACOPF. It's not needed actually, because we don't need anything. The sensitivities are there to basically, obtain the different power flows and everything. So we don't have to solve it like for continuously the ACOPF. It's like for a time block you can solve, and each time block we can solve it. And obviously, like, I want to know what are the actual power flows and the system. At that time we solve it. Okay,
Okay.
so now let's see how we can write this particular program. So can you make the screen like plus? It's 100% visible. No, not like this. That percentage, can you increase? No, above 100% is mentioned just below my photo. Yes, yes. More, more. Yes, how it's visible, right? I don't know. Okay, so you can zoom in just to see the like, entire code. So first of all, if we look at this particular code, this actually I have already written it down, and I have done some basically calculations here. So I asked you to do some basically, like, convert everything into per unit and verify whether the solution is right or wrong. So you can do it. So first of all, let's talk about how we are going to verify whether our solution is right or wrong. That is more important, I think. So if you are using MATLAB, I would recommend you basically a function or basically a file, like, you can look for MatPower toolbox. So it is a free open source tool. Okay, so you can simply go there and download the latest version, and it's a piece of code, so you can download it. That is available, and let me see if I have it. So MatPower, if I search, yes, this is what inside that particular download. Okay, so it is basically a piece of code only, and there is no exe executable file. It's again MATLAB code only, so this install matpower.m file you can only open in MATLAB, and it's because .m file, and once you run it, you are able to basically uh, install, you can say, or basically add the matpower into your MATLAB. Once it is added, I can perform multiple, like, this operational things. So, like, let me write it here. Let's say run DC OPF, and if I have this case 5, I can type in, and it will run DC OPF for me. So whatever DC OPF code we have written, we can verify whether we are getting the same results or not, and this is how we can verify. So we should get voltage magnitudes equals to 1, so that is DCOPF, so it is already equals to 1. These are the angles in degree, so we are getting that angles in radian, so we have to convert them into degree and see whether we are also obtaining the same results. Then these are the P powers. So for generator 1, generator 2, it is 0, 3, 4, and 5. Some powers are available. And then we have these loads are already known to you. Lambda. So the dual variable with respect to the equality constant should come equals to this value. This is how we can verify. Apart from that, you can say that, like, for different branch, what is the active power flow and what are the basically reactive power flows, which is 0 in case of the DC. Otherwise, for ACOPF, we can get those as well. Then what are the generation constants, like which generations are basically limited? So these two generators are at maximum capacity. So it's like at 40 and this is at 70. And we are not considering any power flow limit so far. So that's why there is no limitation or uh, uh, power flow constants. If they are not violated, they are not shown here as well. Okay. So you can solve it easily. Similarly, we can run ACOPF as well. Let's say for the same case 5, and run it. Okay, run OPF will do the ACOPF, and run DCOPF will perform the DCOPF. So this is our ACOPF. The entire summary is also provided, like how many buses are there, how much the generation capacity, and how much is the losses, loads, and everything is provided here. And but if I look at the bus wise data, these are the magnitudes, these are angle in degree, then these are the power generation, and then different lambdas. So if you see between AC and DC, at the bottom no branch flow constraints has been violated, so there is nothing. So if branch flow constraints are not being violated, it means network congestion component is not there. And we discussed yesterday that LMP depends upon congestion. So if there is no congestion, LMP should be equal. That is also we have identified that case one, when there was no congestion for that three bus system, and the LMP was coming equals to $10 per megawatt, right? And whenever we applied congestion, the LMPs were different at all the nodes. So here you can see there is no branch flow constraint, so there is no line limits. So we can basically check for the LMPs. So here LMPs are 119, and earlier when we performed DCOPF, it was 118. So LMPs are different, but they should come equal. So why this is happening? Can anybody put their thoughts and comments on it? Why the LMPs are in ACOPF is coming like 119, 120, 121 or something like that, and here it is coming equals to 118. This lambda is LMP.
Sir, you said congestion. If congestion is there, then LMP will be different, and if congestion is not there, then LMP will be same. Maybe that is the scenario
No,
here.
but there is no congestion, right? So you can see that, the branch flow constraints. So there is no information here, which means none of the branch is limited. They are all within the limit.
Okay.
So there is no congestion basically in the system.
Yes.
So what can be the reason for that? Like coming out different LMPs. If you see for DCOPF, there is no congestion, which means there is no line flow limits has been violated. If you see here, LMPs are equal. So this is what we basically learned yesterday, that if there is no line limits, LMPs will be equal. So for the three bus system, all the three at all the three buses, the LMPs were equals to $10 per megawatt. Here as well, if you see at all the buses, it is equal 118.737. So that is correct. But for ACOPF, the LMPs are different at every bus. This is happening because of network losses, and it is not because of the reactive power. It is basically because of the network losses. Okay, so there are network losses associated with each and every branch. Whenever there is a losses in a branch, the LMP difference will be there between the two nodes, between the branches, between the two nodes of that particular branch. Okay, so that's why these LMPs are coming different. But if you see, they are not drastically away. They are like hardly one or like $2 per MVA hour. So that is the only variation. So that is because the losses are minimum. It's not as compared to the the consumption in megawatts, hundreds megawatt, or the production in 100 or 150 or 500 megawatt. The losses are hardly like 2 megawatt or 1 megawatt or 3 megawatt. So that's why the LMPs are very close together. But if there is a line flow limit, then you will see that the LMPs are not close. So let's open. Let me open case 5. Okay, and let's load it. dt equals to load case. This load case is basically a function in mat power. So that's why I asked you to not use the load case command and paste all the matrices there, because this is for mat power, because this function is defined in mat power. And if I look at this dt, let's see what it is for the branch data. 400. Okay, and if we are running the ACOPF, what was the power flow? So if you look at the power flows from 1 to 2, it is 300, and then rest of the power flows are less than 300. What happens, just to see the effect of congestion, let me put dt dot branch, the very first branch, and 6 to 8 equals to 300. Okay, so let's put it there and then run dcopf for this particular dt. Okay, and then run opf for this modified values of dt and see what are the results. So if you see, first of all, I restricted that 300 megawatt. Like earlier it was 400 and the power was not flowing up to 400, so we have restricted. Now once I have put those constant, you can see in branch flow constant, earlier there was nothing. Now one violation is basically reported here, that there is a limit of 300, and then maximum power flow is basically reaching to the 300. And by doing so, you can see the LMPs are now different in DCOPF as well, because the congestion is present, and that congestion basically change the LMPs. And you can see the deviation is significant, not $1 or $2 per megawatt. It is basically like 50 or more than like 40-50 megawatts dollar per megawatt is basically the difference in the LMPs. Same thing you will observe in the for the ACOPF as well. So like in for ACOPF as well, there is a branch flow violation is reported, and if you look at the LMPs, they are also different, very much different, because of the network congestion. Earlier they were very close, like they were different because of losses, but very close together, roughly around 118 to 120 or 21 only. But now they are going up to 150, and this is coming like 109 only instead of 118. So they are basically coming different but distinct as well, because the congestion is there. Okay, so these are like inbuilt tools are available in like, so med power is there, and there are, if you read, it's a read only document, you will know that it can perform lot of power system operation related actions are the, you can solve basically OPF, DC OPF, economic load dispatch, and different other unit commitment, and everything like all the power system operation related problems can be solved with the help of met power. But sometimes like to do research, or like to do experimentation, how to use just to play with the entire code, we should know how we can write down the piece of code. So earlier in the morning, I have explained you the use of fmincon for writing the DCOPF program. For DCOPF, we have written a program. Now we will do the same for ACOPF. So here, if you see in the very first line, it is I have taken the input as a like 5-bus system. So 5-bus system input is taken. Now I don't think so I'm going to need these values. So I will comment this one because they are not needed for the time being. Okay. If you look at the line number 10 here, okay. If we need, we can again bring them back, but I don't think so we are going to need them. So I asked you to convert everything into per unit, first of all. So this is how we can convert. So like, at if you open this particular file, so let me open it. Open case 5. So this is the case 5. The demand is given in megawatts only. So first of all, I will convert that into per unit. So I have converted dt dot bus, and we have demand between column 3 and column 4. Column 3 is active power demand, and column 4 is reactive power, QD demand. So I have divided it with the base MVA. So by dividing base MVA, we can convert that into the per unit system. So this is like the demand has been converted into per unit. Apart from that, we have to convert the generation into per unit, but generation is the output variable for us. So we will convert the limits, generation limits into the per unit system. So that is available in the dt dot gen data. So this is the data available, and in fourth column we have Qmax. Then fifth column we have Qmin. So active and reactive power. So reactive power maximum and minimum is available here. Then ninth we have Pmax, which is like active power generation maximum limit, and then active power generation minimum limit at 10th column. So I have divided everything with the base MVA. So I have converted that everything into per unit system. Okay, so all are basically on the same scale now. Then here what we have done is we have obtained the number of nodes, or we can also call them buses. Okay, so this is the length of the bus matrix. So this is the bus matrix. So whatever is the length of this matrix, we can call it number of nodes. I think earlier in the morning I used nodes full, and now here I am using n only. This will give us the number of generators. Okay, so we will get number of generators here. Then this will give me the number of lines or branches. So whatever is the length of the branch matrix, that will give me the number of branches. Then like I've been using dt dot bus, dt dot generator, and dt dot genco. So everything I've been using, like earlier in the morning I used everything. So instead of just to use every time dt dot, we have kept those like as a capital bus, like different variables I have created, and we used those here. So next time onwards, instead of dt bus, I will use this bus variable, and in MATLAB, small bus and capital Bus both are different. So you can see these are the 4 assignments I did just for ease of programming. Now there is a function make ybus in MatPower, so I used it. And if you don't don't install MatPower, I would recommend you make basically, or you can write a piece of code to make a ybus. So ybus is nothing but like at any bus particular, like how many lines are connected, the summation of those admittance basically go into the ybus matrix for that particular uh, element, like row and comma column. And all the off diagonal elements of basically like between I and j, if there is a connection between I and j, then it will be the admittance of that particular branch, and otherwise you can place 0. So that is a very simple, like 2 for loops will be needed, and hardly 5 or 6 lines you can write the code for making ybus. But in MatPower it is already inbuilt, so I called that code make ybus for this particular information. So I have obtained the ybus, so I'm not writing to do this. So this is just like initializing the different parameters which we basically considered here. What are the different parameters? So we have defined everything. We have taken generator cost, so that will give me a, b and c. We have defined bus, so bus will give me pd and qd. Y bus will give me the y ij and theta ij, and power flow max will be taken from the branch data, and pmax, pgmax and pgmin will be taken from the generator data, and vmax will also be taken from the bus data. So everything actually I have initialized so far. So all the parameters basically I have supplied to my particular program. Now next part is defining variables. So we have considered there are 4 variables only. One is active power, another is reactive power, then voltage and angle. So these are the 4 variables. Vi and Vj both are same. It's a voltages, and I and j are just index. So I have defined variables like this. So this is the sequence I have used to define the variables. And so variables are defined like, first of all, I will define angles at all the buses. Then I will define voltage magnitudes and the second phase. And then the third part, I will define the power generation, active power generation PG, and then reactive power generation. So this is the sequence I have adopted. You can define as per your programming logic. It's need not to be the same. It's a programming. The thing is, whatever we have written here should go into the fmin code. That's it. That is the only thing. And I have placed a code that this code is working fine and results are compared with MatPower. So let me just get rid of that, because many times we write some codes and we left them unattended, and after some time they are not working. So that is because we generally make mistakes every time. But I have written it that okay, this code is actually working fine. If some issue is coming, I have to debug that. But this code is perfectly fine. So let me remove this one. It's not needed. That is for my reference only. It was commented. So as discussed earlier, we need fmincon function. So I have defined fmincon function. First of all, I will use a objective function. Okay, so first of all, the function will be given, whatever is the objective function. So I will come back here, line number 18 later on. First of all, we will see the objective function. Our objective function is what? Minimization of cost, CI, PGI. That is our objective function. And if I look at the cost function, it is basically okay, wait. Dt equals to load case and case 5. Let me see the dt. So this is the dt here, and the gen cost is a quadratic cost function. And so 14 and 0.14. So these are like, different values are given here. So this is a quadratic cost function. So that the objective function will be ap square plus bp plus c. So I can go at look at their main objective function. So this is the function which we have defined, which is basically part of the f min code, the very first entry. So this function is the same which we have written earlier in the morning, that for all I equals to 1 to ng I have supplied here. Objective is equals to basically generator cost into x2 node plus I plus x2 node plus I plus 100 gen cost and so on. Now, why I'm using 2 into number of nodes plus I? So that part is basically, if you check what we did earlier, we basically defined a set of variables. So let's keep it here as well. So first of all, angles will come in x. So variables are basically defined in x, and we will have angles first of all. So if there are n number of buses, so let's say for 5 bus system, there will be 5 angles and 5 voltage. So 10 number of variable places in x are basically reserved for angle. Then we have pg. So that is basically 2 into n plus I. So that's why I use 2 into n. That place is defined by pg. And in objective function we don't have qg, so that's why I'm not using that as well. So this is like, a p square. So this is 1p into p square plus bp, and c is 0, so I have not mentioned it. And anyway, it is a constant term, so it will not affect our optimal solution. The solution will remain same, only the function value will be different. But otherwise, like the output variables will remain same. So that's why I have not kept it here so far. And this is, and the second part is basically, if you see, I have commented a line here, the line number 6, and that is basically for if I have a linear cost function. So this part is basically a linear cost function, right? B into P. So for that, I just kept another line so that I will just comment the above one and uncomment the below one, just if there is only linear cost functions. But now we have like quality cost function, so I will keep line number 5 active and 6 as a commented only. So this is the objective function which we have defined. So that's it. Then we have to define x naught, ab, aeq, beq, these, and lbub, let's say, as well. So we know that a and b are empty, aeq and beq are also empty, so those are already defined. We don't have to give too much time there. Now let's define x naught, lb, and ub. So first of all, I will define, instead of like this, I should, generally I define ub above x naught, so that I can visualize that x naught is between LB and UB. So x naught is our initial gas. So initial gas should not violate the limits. That should be within the limit. So that's why generally I define like upper bound, then below lower bound, and in between UB, so that I can see that okay, everything is within the range only, because this is my initial gas and I should not be the wrong. Like I should not supply a wrong initial point. So first of all, we have to define angles. So the upper limit on the angle is only pi and minus pi. So we have defined pi, and sorry, we have defined pi multiplied with ones into 1 by n. So n number of pi's are defined for each bus. We have defined like the upper limit is pi, and similarly the lower limit for the angles are minus pi. So that is also defined here, that the angle can vary between pi to minus pi. And the initial gas is already defined, that initially it should be 0. We assume that voltage magnitudes are 1 and angles are 0. So this is what we have defined. And we have to define voltage maximum value. This is my second variable is voltage. So voltage maximum value is basically taken from this our input file. See this bus data, the minimum value is last one and second last is the maximum value. So the maximum value is 1.1 and minimum value is 0.9. I will take those as a input, and as I have converted everything into per unit, so I will use those values, and I will go here as a main objective function. So this dt dot bus 12th column will give me the voltage maximum value, and similarly the 13th column will give me the minimum value. So that is the voltage maximum, upper bound and lower bound has been defined. And in between values are, obviously we assume the flat start, that is 1 angle 0. So the angles are defined 0. So I will define 1 as a voltage. So 1 per unit is the voltage. So 1 into, and then number of nodes as per the number of nodes. Then we have PG. So PG maximum value and PG minimum value. Similarly, QG maximum value and QG minimum value will be defined here. And everything I have kept at 0. That all the PG and QG are within the limits and they are at 0. Okay. Sometimes what happens that a generator minimum limit is non-zero. In that case, you should assume whatever is the in-between value, and you can generalize that as well. But let's say it is 0 first of all. So maximum value will be available at in generator information. 9th column will provide you P max. Okay, 10th column will provide you P min. 4th column will provide you Q max, and 5th column will provide you Q min. So this is what I have placed here, that 9th column will provide me PG max, 10th column will provide PG min, then 4th column will provide Q max, and 5th column will provide Q min. So this is X naught, LB, UB, A, B, and AQ, BQ we have already defined. So this is it. Then I have defined some options as well, that for algorithm I'm going to use interior point and display the number of iterations. Earlier, like if you've seen, I used display off, that do not show me the iterations, but here just I want to see the iterations. So it's again like choice. I wanted to do something else, so that's why I needed them. You can get rid of them as well, still you will get the same answer. Okay, so we have defined up to this particular part. Okay, so this part has been defined. Now let's define the nonlinear constraints. So everything else has been defined. These constraints are needs to be defined. So if you see, we have defined our objective function already. We have defined our generation limits, our voltage limit. This is one equality constraints which we could have defined with the help of AEQ and BEQ, but as we did it like in DCOPF as well, that we can provide that in the non-linear constraints as well, whether it is a linear constraint, but we can still define it in the non-linear constraints. So these two are basically the non-linear constraints which we are going to define. For this particular demo, I have assumed that there is no line congestion, so I have not written like this particular condition in the code. But Kush, please create assignment. Okay, and I will explain you what is needs to be basically done. I will supply this one, and they just have to simply modify a certain piece of code. So in nonlinear constraints I have defined here. So it is still a good piece of code and very robust one. Like I needed only one loop and everything. So this is like C and C eqr. C is the like inequality constraints, C eqr equality constraints. So as I told you that for this particular demo I haven't uh, defined inequality constraints, but we have one nonlinear equality constraint, which is this one, line flow limits, which I have assumed that I don't have any line flow limits. You have to define that. So that is your assignment. And here I will just explain you how equality constraints are defined in MATLAB. So first of all, I will come here. So you have to get rid of this C empty. I provided that, okay, I don't have any limit. So I provided as an empty matrix. You have to define it. Now for so the active power balance and reactive power balance equation has to be written down for all number of nodes. So I have used a for loop I equals to 1 to number of nodes. So that is one part. Next is I have basically used a find command that in branch whether ith node is on. So like in a particular branch, if I okay, I have a question for you. Let's say can you see this particular table?
Yes, sir.
Correct. So what information we are getting from this particular table? Simply connectivity,
Bra-
that a branch
Yes,
is
correct.
connected between two nodes. What is the
That too.
reactance, Rx and B, and the line flow limits. This is the information we are getting from it, right?
Yes.
So somebody was asking whether a line is on and off. So you can see this status is basically 1, which means this line is on. And if you change it to 0, it means this line is out of for service or out of service basically. So you can remove that as well. It is doable in
Okay.
MATPower. But
Yes.
no, like if I'm just for teaching point of view ACOPF, I don't need too many binary variables to complicate my code. So that's why we are assuming everything is 1. Okay.
Mm.
In MATPower, you can easily change it like 1 to 0 and solve it. It's fine. So what will happen if so the very first branch is 1 to 2. If I make it 2 and this one as a 1, will it change the information provided? Or will it affect my solution?
Based on this data, I don't think it will affect the solution because
It's
we
a,
are not.
yes, this is the first branch, and it doesn't matter whether it is the first branch. Let's say move this particular branch here to the bottom. So we control Z and control. Will it make any difference in the data? Or whatever the code we have written, will it make any difference?
Sir, Y-bus matrix would be different.
Y-bus
No,
matrix will not. Okay,
will
that's
not.
very good because if Y-bus matrix is fine, then I think our entire code will also be fine because that branch data is only we are extracting from the Y-bus matrix.
Okay.
So will it make any difference what I am providing? The answer is no. I'm still providing that there is a branch connected between 1 and 2, but instead of 1 and 2 I have written it 2 and 1. That is fine. Okay. and that branch has a resistance and reactance and susceptance of the information given. That branch has a line rating of this, so it will not make any difference if I change it or not. Okay, so but like usually we are basically uh, look the entire code are basically the way it is there. So for the sake of simplicity, we are basically just keeping I'm keeping it as it is, but it will not affect your code. So I have to look at each and every, like while writing a generalized piece of code, I have checked whether the branch or the node 1 is available on this side or this side. So I will check it for both columns. So if one is written here instead of here, still a line is connected to bus 1. So there is certain power flow. So I have to write down that Pij, this Pij for that particular line as well, right? So Pij will be given for all the lines, whether it is in from or whether it is in to. So it should not make any difference. So that's why we have written it our code like this, that I will check the availability of I in first column and in second column, both the columns. So we are basically looking, find means we are looking of I, that what are the different connection of a particular node I in first column and second column, and I will keep them in like RF or RT. So whether it is RF like from or whether it is to. So this is what I have kept it here. Then I will also look whether there is a generation at ith bus or not, because if there is no generation, uh, this PG and QG is not needed for those particular generators. So what I will do is I will also write it like this, uh, that I will check whether the generation is there or not. If generation, let's say in generator matrix, if I see here, where is the generator matrix? Here. So there is no generator at bus number 2. So we should avoid that as well, right? Now, next part is, so we have mentioned this. Now I will write the two different codes. One is R1 is empty. If R1 is empty, it means there is no, like, this R1. If it is empty, it means there is no generation on that particular bus. So for that, I will write it differently. And if R1 is present, I will write it differently. Okay, so this is what, first of all, let's say for the very first bus, we have a generator there. So I will see how can we write it. So if you look at this particular part, I have written an equation that if there are multiple generators, so we have two generators on the bus 1. So that R1, which basically we will find of the generation which are available in ith bus. And what was the X number? So let me copy again for you. Our variable number for the PG, it was after the angle and voltage. So we have 2 into n number of, sorry, here 2 into n number of angles and voltages. So after that we will get a PG. So I have placed PG there. So whatever is, like, suppose if there are two generators, that number will come here, and respective variables I have added. So it is like, if there are two generators at bus 1, so the formulation will be basically PG1 plus PG1. There are two generators on the bus, so there are two PGs. So this is for each node. It is not for each generator. For each node, if there are two generators, I have to add both the generators and then put PG here. So this is what we have done here. Then same we will do for the number of reactive power as well. So reactive power will start after n number of angles, then n number of voltages, and then ng number of PG, active power variables. This is what here we have mentioned, like 2 into n plus ng. These are the basically variables, and after that the index for reactive power will be there. So that's why second equation is for the reactive power. Then I will again write it down the same thing, like same equation, where I have to put Pij, and Pij is what? Summation over j1 to n vi vj yij and cosine of the theta ij minus delta I plus delta j. So if that everything is written like this. Here you can see that Ceq and whatever is the earlier we have defined. So this Pg and Qg has been defined. So here I have been basically whatever is the summation of Pg. So this is earlier is Pg plus Pd. Okay. So I have used a negative sign. So basically we have moved these two on the other side. So this will be positive, Pd will also be positive, and Pg will be negative. Okay, so the entire equation is moved to the right hand side. So this is what I have been mentioned here. So it's like Pg is negative. Now Pd should come equals to positive. So this is the Pd. Third column in the bus matrix is my Pd. So it's minus Pg plus Pd. Then we have Pij. This entire thing is Pij, and Pij, it is not Pij, it is sum of over j and vi vj yij cos theta ij minus delta I plus delta j. So this is what basically you can use a loop if you are not comfortable with this kind of writing, but instead of writing a loop, I have used a single line expression that vi basically we have taken out. So this is vi because starting endpoints are basically angle, and then ith point will be the voltage. So this is vi multiplied with summation over, we have summation over j. So what we did is like a matrix multiplication and then summing the vector, and this is what we have done here. So summation over x n plus 1 to 2n, so that is vj. Then dot product of absolute value of y bus, and that will be like I is fixed. Am I muted? Okay, fine. So this is absolute. So y bus magnitude. So I is fixed and j is varying. So that's why this I is fixed and j is varying here with this column. Then can you a bit zoom? Because these students are not able to see it. Okay, so then again dot product and cosine of this thing. So cosine of angle of y bus and which elements only? Ij elements. So I is already fixed and j are basically we are taking as a entire vector. So we are multiplying each element and then making a sum over it. So then it is xi. So xi is delta I. Delta I is the very first element angle. So this is delta I, and delta j will be again x over 1 to n. Okay, so this is my active power balance equation. In reactive, I will repeat everything as it is, but with qd. So qd is available at the fourth number location, and we have this equation with a negative sign, and instead of cosine it is sine theta. So this is what we have mentioned here. So one minus sign here, and then instead of cosine it is multiplication of the sine and angle of the same thing. So and our rest of the things are same. So these are basically equality and inequality constraints, sorry, equality constraints. And then it is if condition. Yes, if you have any questions. Okay. So another thing is, like, I will look for the reference bus as well. So like for each I will check whether it is reference bus. So if bus comma I comma 2 is equals to 3, so 3 represents reference bus in the second column of the bus data. So if it is 3, I will put and one more equality constraints, and that I have placed at the end of the equations, like, at, so I will need at one for active power, one for reactive power. I have, let's say, 14 number of uh, nodes. So 2 into n, so like 28 active and reactive power balance equation. So that's why I have kept CEQ equals to 2 into n plus 1. So it is 29th equation I have placed, and that is angle equals to 0. So this is only angle. So this means it is angle equals to 0. Uh, Suppose if you want to fix voltage of the slack bus as well, you can use this particular equation which I have commented here. So let's say if I want to fix the voltage equals to 1.05, I can do so. Generally, we do not do it. So that's why I have commented it here. And then we will solve it. This is how we can write down the non-linear equation. If you have doubts, please ask me. So you have to change your assignment. Just listen. You have to change this non-linear constant, okay, and add this part. So the assignment I will place here as well. Like, this is your assignment. Add inequality power to limit only on line 1 2, and PF 1 2 max should be equals to 300 megawatt, as we already like seen the results for 300 megawatts. So we will put 300 megawatts. So 300 megawatts. So this is your assignment. Okay. Now we have solved it. Control save. I will go back to my main program, and I have placed it, and I will run this particular program. Let's see. Let's hope there is no error. So yes, it has been executed. So let me see again. Let me stop it here so that I can visualize everything. So we have, so I
Sir,
have
is
started,
that
and
sir is
then
Mat,
yes,
but is that for to run this program?
no, mat power is not required.
Okay, only
For
Fmincon through Fmincon it will solve.
no, I think I have explained you that
This.
this information you can paste directly from the case file. So this file I will supply. So instead of like
Okay,
I use dt, so this mpc should be replaced with dt, and all these four, like bus data, generator data, branch data, and cost data should be pasted here, this particular location, right? So then it has been loaded basically. After that, one thing you have to do is you have to make a Y bus. Okay, so you have to make a Y bus, and you can simply Google that how to make a Y bus. You will get a program as well for that, so you can use that program, make a Y bus, and you can directly put the Y bus here. Okay, after that you don't need mat power. So I just use these two commands, like load case, like just to copy, and I don't want to copy and paste everything here. so I use load case, and as it is available there in MatPower, so that's why I used make y bus. But you don't we could have easily programmed it as well, like it's not big deal, it's hardly a few lines of code. Okay, so next part is, okay, let's see the results, right? So let me continue and complete the execution and see at the results. So these are the different iterations. Local minimum found that satisfy the constants, and these are the different x values, and then I have calculated theta. Theta was angle. Angle was placed at like we defined it in the very beginning, and the 5 buses were there. So this x is my solution. So these 1, 2, 3, 4, and 5. These are angles. So this everything has been converted into degree. So this theta cm is nothing. It's same, but in degrees. So these are available in radian. These are available in degrees. So this is it. Then next part was voltage magnitudes. So voltage magnitudes were 5 voltage magnitude because we are solving it for 5 bus system. So 1, 2, 3, 4, and 5, and you can see these are basically I have placed them exactly the same values. Then if you see like powers, so powers are placed like 1, 2. So this is generator 1. So this is like 40 and 170 megawatt, and then we have different values like 151 and okay, 151 and 143. So these values are available here. So I have kept them here. Then these are the reactive powers. Last 5 are the reactive powers. Apart from that, I have basically uh, taken the LMPs as well. That what are the LMPs? See in this particular code, I have this is how I basically converted everything. So from this XM is my actual output, and from that we have converted radian to degree. Voltage are basically in per unit only. Then I have obtained the everything in per unit. So I multiplied with the base voltage so that everything is again converted back into the megawatts. Same is for the MVR reactive power, and these lambdas are also in terms of like dollars per unit. So I have again converted that into the like dollars per megawatt hour. So these are the lambdas, which is LMP, and this is what we have obtained. Now let's verify whatever we have done is right or wrong. So we are running OPF and case 5. So this is MatPower by which I can verify my results, and let's see if we are obtaining the same results. So by looking at the lambda, we can easily verify. So it is what 119, 20, 21, 20, and 18, and the same values we are getting here as well. So this is the code. So we have written. Now you can use this code to like manipulate the like if you want to add your own piece of code with it, it's completely doable. Okay, and you can easily use this particular code, and it is equivalent to whatever written in MatPower. But again, MatPower is very robust, and we try to use the like get the similar answer. So if you look at like how much good is the answer, like up to like each precision wise, if I talk about, let's talk about the angles in degree. It is 3.523. So let's see what we have obtained. So it's a 3.52 and 27 is basically 3. So this is exactly same values. So we have obtained the same. It's like, for generation 1 it is 170 and 40 is 210. So this is what at the bus number 1 there are 2 generators, so it is 210 only. Is this clear so far? If you have any doubts, please ask me.
Sir, you have explained it very beautifully, but coding it would be require knowledge of a power system as well as uh, MATLAB syntaxes as well. But I have learned MATLAB and power system fundamentals. I have learned a lot before.
Mhm.
Right now, I'll try to do the assignment and
So look, one thing is very important. How can we model HVDC lines and FACT devices? So to be very honest, I have not tried that one, like to model HVDC lines, but I think so far in we cannot do. Okay, there are obviously certain ways by which we can handle those. Like some okay, everything is mathematics. It's nothing more than that. So if maths is available, we can incorporate that. But I have like always working on simple power system operational fact, and I never wondered that how we can incorporate HVDC and fact devices in optimal power flow. In some other problems, yes, so I have certain idea about it, but I never tried to look at the mathematics behind those fact devices and all. And if it is known, it is just math, nothing else. It's only mathematics, and if mathematics is known, we can easily incorporate it. But like to give a proper answer, uh, for OPF point of view, it is not basically like not in the scope of this course as well, and also like I have never tried it, so I will not be in the position to answer this particular question. But yes, we can do it. That is, I'm pretty much sure. Anything else you want to ask, please? One important thing is like programming is, some says that okay, then we know C program, we know MATLAB or Python. It's a programming language, not programming. C, Python, MATLAB, they are basically programming languages, not programming. Programming is just executing the logic, and logic comes from within you. Nobody can teach you the logic. You have to apply logic, and generally we try to like our human nature is we try to find ways by which our efforts are less. है ना? We call it jugaad in India, right? So it's basically like we try to find out ways by which we can put less efforts. So sometimes like doing the same thing, like the piece of code which I have written to write down the power balance equations. It was not this much neat and clean and this much small. I used to I'm like in the very first time, maybe I could have written 100 lines of code for that one. Over time, I came like mm, the- like every time you have to write down that much long code, it takes a lot of time to execute as well. So over time, we learn a few things, and we are basically able to shrink it. Okay, so that is again like practice will improve your logic, and when you write down the same thing like repetitively, you will be tired, so you will find out some ways to sort that thing. That is human nature. So that's why that code was a simplified one and easy to understand. I will share that code with you so you can easily use it for your further research, or maybe faculties are there so they can use for teaching and lab experiment point of view. It's a completely fine. It's OPF. It's nothing property rights there. So I will share that code. What I want from you is very important. I haven't included transmission line congestion constraint. So that assignment you have to provide. Okay. And I know it is very easy. I have that code as well with me, but I will not share that code, and because it is hardly 2 lines. So you can easily add those lines, and you use your own logic and try to keep it as generalized as possible, that you don't have to like, whenever, let's say if I say that the congestion in instead of line 1, if the congestion is line 5, you don't have to type anything. Let's say input data, obviously in input data we will change the congestion from line 1 to line 5, but your code, whatever is the like nonlinear constant function, should not need any changes. It should understand that okay, once the load case has been done, then nothing should be basically supplied after that. So in the case, basically case file, we can do many changes. That is like providing the input, but after that you should not perform any more addition in your code. So that is what I call generalize. There are further generalized code, like, which gives you the message that okay, this is where it has been went wrong and all, but like, let's keep it the very simple as well. So I want you to supply me like the code, and the deadline we can keep, I think. So today is Friday, right?
Yes.
Friday and Saturday we have a quiz. Okay, so far up till until today, whatever we have discussed in this FDP, a quiz will be conducted tomorrow. The timing will be 30 minutes to 1 hour, and it will be available on Canvas. Okay, once the link is being opened, it will automatically, the submission will automatically terminate after that, given like the timing is 30 or 40 or 50 minutes. After that time, it will terminate automatically. So you just use or basically sit down on that particular quiz when you are completely free. Okay, and it will not open again. So let me tell you this thing. And 2 to 3 is officially we have given time for the quiz, but it will be open for the other, like for quite some time, like 2-3 hours. So if you are not available between 2 to 3, you can basically uh, start complete that quiz either before or after. Okay, but it won't be like a day's flexibility, hardly like push. I think we should keep it open from 1 to 5. That will be fine, I think. That quiz. So we will keep it open from 1 to 5. So 2 to 3 is like official time in which you can do, or if you can or start operating at 1 o'clock, then you can complete it by 2 o'clock. Then 2 to 3 is free for you. Let me tell you that 3 to 4 is our official again class. So after that class, again 1 hour is there, in which you can, if you not was not free at that time, you can do it in the evening hours as well. So yes, like 1 to 6 it will be open, not more than that. Okay, so you can start working on that like around like 4 or 5, then you will be able to complete it by 6 p.m. maximum. Okay. If you have any doubts, we can discuss here as well. Like the students here available, you can also ask doubts in between. It will be good for the other participants.
Sir, how the congestion in network basically avoided can be avoided, or what are the tools that we can use to avoid congestion in our network?
What are the tools to do what?
Eliminate the power congestion, sir.
So
Means it is basically if commercial load of higher amount is added, then there may be congestion in the power lines. Uh, but what can we do to basically alleviate this power congestion?
So if there is a congestion, so it's a like a very simple question. And let's say a wire is there. I have a load. If I want to use that particular load, some current will flow in that wire, and let's say it reaches to the capacity of the wire. So that is congestion, right? So first of all, we
Okay.
should focus at what is congestion. So that is congestion, like going up to the limit.
Limit below the thermal limit.
Yeah, at close to thermal limit. So that is our limit has been reached. If I want to reduce like line flow below to the whatever is the maximum limit, there are ways. Basically, either economically you can manage. So management is from different point of view. So from system operator point of view, it can ask load to reduce if it affects the security of the system. And the first of all, one thing is, system operator, what system operator can do its own level, it can basically use the fact devices to manage the active power flow on those particular. So like with the help of like injection of the reactive or consumption of the reactive power, we can change the active power flow limit of the line to some extent, not to large extent. If it is congestion is there for like every time or entire duration, and it is violating, like all the time we have to the limit is violated or not violated, I would say it is always, the line is always on the maximum limit. It means that corridor is basically uh, adjusted, and we have to increase the power flow capacity of that corridor. So one long term solution or answer is uh, one long term solution is to build new lines. Okay. And short term
Yes.
solution is to use fact devices. So these are the two ways by which we can increase the line capacity. Another way is, instead of increasing the line capacity, we can ask loads to reduce the like ask loads in such a way that the power flow in that particular line is being reduced. That we can do by providing the economic signals. So let's say power is flowing from A to B, and that line is congested. Then
Demand response techniques,
demand
basically.
response basically same. Like if we increase
Yes.
the prices, the consumption will reduce, and if consumption is reduced, then the flow will be reduced. So that is basically economic signals we can use to reduce the congestion. Another way is basically just to increase the line flow limits. And I asked you, like that, like there are two ways: short term and long term. Long term is increase the line capacity. It will take time. System operator has to build new line or upgrade the existing one. But another way is use the fact devices. Yes, these are the two techniques. So generally, we like, from research point of view, congestion management research, we look at the short term solution. Long term solution is quite easy to say. Yes, everybody knows that you have to build the new lines. But if something is congested right now, what are the different course of actions which a system operator can take to manage the congestion? So that is another thing. Okay.
Thank you, sir.
Yeah. How much difference may come in results between DCOPF and ACOPF? Very much, basically, because DCOPF is very much different from the ACOPF. Okay. So there is no reactive power flow, there is no losses. So the difference is basically equal to the number, like, a difference in terms of what. First of all, we have to see whether we are talking about the voltage, whether we are talking about the angles, uh, objective function value, or basically we are talking about the prices lambda, that derives the entire economy. So who will be paying how much? So these are the different questions. And how much difference is, like, for this particular system we have seen the DCOPF prices was 118 point something, and for ACOPF it was 121 maximum and 118 minimum, I think. So this was the difference, but it is not fixed. It varies from the network to network and scenario to scenario. So this is it. Okay. Okay. Any more? Do you have any other question? So tomorrow the classes, this is our, I think, first Saturday. So the classes will be 5 hours. First is 10 to 11 is one lecture from an industry expert. She will be going to talk about EV charging stations and policies related to that, how the open access charges will affect. So about those aspects. Then Professor Bhakar will take the classes about smart grid and digitalization, demand response as well. And so the timetable is a bit shifted as per the availability of the faculty, and as per our ongoing classes as well. So somewhat it has been moved, something has been moved here and there, but that timing is fixed. Saturday it will be 10 to 3 hours, so 10 to 12 and then up to 1 to 2 is the break, and then 2 to 4, that is 5 hours on Saturday. Then Monday to Friday next, we again have 10 to 11 mandatory, and on few days we have 11 to 12 as well, because just to accommodate that 26th like holidays, classes. And then in the evening it is 2 to 4, that is always there. Okay, so that's it. I will update every day on the WhatsApp group that what are the class timings, just like if you are confused with the timetable provided. This is it, I think. Thank you very much. If you have any further questions, you can email me. I will try to answer you on email as well. Thank you.